Hi, folks, welcome back. Today, I want to take a look at a paper that asks the question: how can we design APIs such that programs that are built using those APIs scale well to multi core processors? And in asking that question, the authors propose a rule called the commutativity rule, which, if APIs follow, they will end up being scalable to multiple cores. Now, the traditional approach for testing for scalability has been focused on a specific implementation. You choose a particular software and a particular workload for it, and then you measure how it performs as you vary the number of cores. You would typically do some sort of profiling to see where the scalability bottlenecks lie. Now, this can tell you about the scalability bottlenecks of that specific piece of software. But what the authors of this paper want to investigate is how can we look at scalability at the API level. The goal is to be able to reason about it before an implementation even exists, just by analyzing the properties and specifications of an API. The basic idea is quite simple. If you have a series of operations where the ordering does not affect the final results, or in other words, they are commutative in some sense, then you will be able to parallelize them across multiple cores. This is the same thing as saying that the memory accesses of these operations do not conflict with each other. This idea makes a lot of sense at an intuitive level. What the authors are trying to do in this paper is formalize this idea and make it more concrete and more analyzable. If we take the strict definition of commutativity from mathematics, it is too stringent to be useful for most real software. One of the central contributions of this paper is their definition of a type of commutativity that is state dependent and monotonic. This tries to capture the idea of commutativity as it would apply to realistic software and still be able to reason about its scalability to multiple cores. So let's try to be precise and introduce some notations. We model a system execution as a sequence of actions, and actions usually come in pairs. They consist of an invocation and a response to that invocation. The authors use these left half circles to represent an invocation and these right half circles to represent the response for that invocation. Different colors represent invocations on different threads. A specific execution sequence is called a history, and a history is well formed if all the invocations and responses are correctly paired off. For example, in this history, if you look at the red thread, you'll see that A is paired off, as is D, as is H. And this is true of the other threads within this history as well. We use this notation h bar t to denote that part of the history that comes only from the thread t. So if we want to formalize the idea of commutativity, we want to somehow express that the order of actions does not matter. If you look at a prefix of a history, you want the later actions to be indifferent to the ordering of that prefix. With that in mind, let's define the notion of a reordering. H prime is said to be a reordering of H if the thread restricted history of H and H prime are the same. This is essentially saying that H and H prime contain the same actions but may have other threads interleaved among them in different orders. For example, this is a reordering of this, because if you look at just the red thread, A comes before C. However, this is not a valid reordering because C comes before A. And this brings us to the notion of SI commutativity, where the SI stands for state dependent and interface based. If H is the concatenation of two sequences X and Y, we say that Y SI commutes if you can reorder it to Y prime and then follow it up with another sequence Z and the sequence X, Y, Z as well as the sequence X, Y prime Z are both well-formed histories. The way to interpret this is that the action sequence X puts the system into an initial state. We consider reorderings of Y to show that we are indifferent to its order. And finally, we suffix the history with Z to capture the idea that any later events cannot tell the difference between the two reorderings of Y. So that captures the idea of defining a version of commutativity that takes state dependence into account. But it still misses one thing, and that is a monotonicity property. It is still possible for a sequence y1, y2 to be SI commutative, even if the prefix y1 on its own does not. If you look at, for example, this sequence where the red thread sets a value to 1 and then 2, and the blue thread simply sets a value to 2, no matter how you reorder this, the value will end up being set to true. So this entire sequence is SI commutative. But if you look simply at its prefix with A and B, it is not commutative. Basically, future operations can decide whether this subsequence is commutative or not. And so we strengthen our definition of commutativity by including this monotonicity property, such that if Y is sim commutative, only if any prefix of Y is also SI commutative. And this property captures the idea of operations being able to commute under certain conditions. If you look at most realistic APIs, they will not unconditionally commute for every combination of inputs. But given some constraints on their inputs and their sequence, they might commute. And this is the idea that sim commutativity tries to capture. With this in mind, we can come up with some high-level design guidelines for how to design scalable APIs. The authors over here look at POSIX, or the Unix system call API. One common source of bottlenecks is highly composite operations. So we should decompose large compound operations. The classic example of this is fork, because it creates a new process but also clones the existing one. And because it recreates so much state, fork does not commute with most other operations. Another guideline is to not be too specific when defining your interfaces. POSIX encodes the rule that it will return the lowest available file descriptor for many calls. And this means that if you open a sequence of files, that's not going to commute because the order in which they execute determines the number of this file descriptor. This is an example of an API being overly specific. Most callers of this API don't even actually care that the file descriptors follow this rule. Now we come to the part of the paper where we try to use this new commutativity principle to actually reason about concrete real APIs. The goal is to be able to use this new rule to automate reasoning about the scalability of an API. The authors have built a tool called Commuter, which takes as input a Python model of the semantics of an API and consists of three phases. The first phase analyzes the Python model and outputs the conditions under which the given API will be commutative. At that point, a programmer could read those conditions and try to follow them when actually implementing that API. But you could go a step further and generate test cases which checks a real implementation. And when they are actually executed, you can look at the memory trace of those tests and issue warnings when you detect conflicting memory accesses. For example, this is what a simplified Python model of the Unix rename system call would look like. And given that model, Analyzer would be able to tell you that if you had two rename calls, A, B, and then C, D, these are the conditions under which those two calls would commute. And their test gen tool would actually be able to generate test cases that exercise those conditions. To show the usefulness of Commuter, the authors took 18 file and process based system calls from Linux and built a Commuter model for those. Based on those models, Commuter generated about 13,500 test cases. And what they found was that only about 9,300 of those 13,500 test cases were able to scale. This shows how, even when in principle an API is able to scale across multiple cores, it's very easy for an implementation to unintentionally sneak in data dependencies that then end up becoming bottlenecks. With this in mind, the authors developed a new operating system kernel called SV6, which has the same semantics for these system calls, but is able to commute and scale in almost all of these cases. So that was a look at a paper that tries to define a rule for how to analyze software APIs to see if they would scale across multiple cores. The central contribution of the paper is their definition and formalization of the idea of sim commutativity, which allows us to reason about complex and stateful APIs found in real software. They apply that concept to a tool called Commuter, which lets you build models of APIs and then analyze them and generate test cases to exercise those commutativity rules. I hope you enjoyed that, and I will see you next time. Thank you very much.